Now let's look at inner products. We've already seen norms. Inner products also gives magnitude of a vector, but it takes in two vectors. So it's not just a single vector. It takes in two vectors and gives a corresponding magnitude corresponding to it. Okay, so let's systematically define an inner product. Let V be a vector space over F. The inner product is defined. Domain of this is the Cartesian product of V cross V, and the range is F is an inner product if for all x comma y belong to the vector space, first it has to satisfy the non-negativity property which we had similar to norms, non-negativity. Then we have 1a, which is the positivity property. The inner product of a vector with itself is 0 if and only if x is equal to 0. This is known as the positivity property. The next property is the additivity property. So we have three vectors. So here it is not x, y belonging to where the vector space, x, y, z. So if we have two vectors, x plus y is the sum of two vectors, and similarly we have z. If we're taking the inner product between x plus y and c, the corresponding output will be the sum actually gets distributed over the inner product. The inner product between x and c plus the inner product between y and c. This is known as the additivity property. Then we have something known as the homogeneous property. So we're scaling a vector, first vector, and then we are taking the inner product between cx and y. Then the corresponding output will be c into inner product x and y. We have to note here that if you look at homogeneity property, which we had for norms, there we had a modulus outside. So here we don't have a modulus. That is something to note. There's no modulus. Okay, homogeneity. Then finally, we have something which is known as the Hermitian property. So inner product between x and y is not same as the inner product of y and x, but since we are dealing with complex fields, it is actually the complex conjugate of y inner product x. This is known as the Hermitian property. So if all these properties are satisfied, then we have a valid inner product. Okay. And there are multiple inner products which we can define like this. Now let's look at our lemma. This lemma says if we have an inner product or a vector space V, then the inner product of x comma x whole raised to half is a vector norm. So what is the consequence? Norm only. So whenever we have an inner product, we can easily find a norm corresponding to that vector norm, and it's valid in vector norm. So let's try to prove this systematically. Prove one is what is known as positivity. What we have to prove? We have to prove norm of, yeah. So how have we defined the norm? Norm of x is defined as x all raised to half. This is how we have defined the inner product, right? Sorry, the norm using the inner product. So what is norm of x? Of x is x dot all raised to half is greater than or equal to 0. How? By the definition of inner product, because norm of x is always greater than or equal to 0. So if you take the square root of that, it will be again greater than or equal to 0. This is by definition. By definition. Similarly, 1a is also by definition. Norm of x is half equal to 0 if and only if x equal to 0. How? This is also by definition. So non-negativity and positivity is already satisfied. Now we have to look at the homogeneity property. So for that, we have to prove norm of x, norm of c times x is equal to modulus of c times norm of x. So let's look at this. What is norm of c times x? Okay, this is cx all raised to half. Okay, so let's look what is the inside term. So let's say cx comma cx. We need to find this, right? Huh. So let's treat this for the time being as some vector y. So cx comma y same as c times x comma y, right? You don't have any doubt with it. The next question is, how do you find x comma cy, right? But we know x comma cy is same as the complex conjugate of cx is according to the Hermitian property, right? So we have c conjugate. Now this is c into c conjugate into y comma x, the whole conjugate, right? So this is c star xy, because xy conjugate is same as xy the whole conjugate as yx is whole conjugate same as xy. So if you have a scalar in the second vector, its corresponding output is c star xy. So this is a result which we can use here, like in inner product between x and cy is c star xy. So we'll use both these properties here. So we'll eventually end up getting c times x comma cx, which is equal to c into c conjugate x comma x. But what is c into c conjugate for a complex number? It is modulus of c the whole squared. Okay, right. So we know what Cx, the inner product between Cx and Cx is. So we have norm of Cx is C modulus of C raised to half. This is a positive quantity, modulus of C, so we can take the square root. So this is modulus of C into x. X raised to half, which is basically mod C times norm of x. So hence it satisfies homogeneity property also. Now the last property is triangle inequality. For that, what we have to do, we have to find norm of x plus y, right? So by definition of this norm, it's derived from the inner product. This is same as, let's treat the square of this. This will be x plus y, x plus y, right? So we already know we have an additivity property, right? X plus y, excuse me, and z. For the time being, let's treat this vector as z. Okay, so this is inner product between x and c plus inner product between y and c, right? Now we can substitute z back. X plus y plus y, x plus y. But we don't know a property of norms like this, so we have to take a conjugate. This x norm of x comma y is same as x plus y. This norm conjugate plus x plus y comma y conjugate. So we know how distribution works for these if the sum is in the first term. Okay, this is same as we can distribute x here. That's the inner product between x and x plus inner product between x and y whole conjugate plus norm of x inner product between x and x whole conjugate plus inner product between x and y plus inner product between y and y whole conjugate. So what is a plus b whole? So you have two vectors. Let's say we have two complex numbers, z1 and z2. What is c1, c2 whole conjugate? The same as c1 conjugate plus c2 conjugate, I suppose. There could be some mistake. This is conjugate plus conjugate plus x plus y comma y, the whole conjugate. This is a positive quantity. All of them are in fact positive quantities. Okay. It is the real line, right? X, it's the inner product, so it is between the real line. So you can actually neglect the conjugate symbol here. What you're left with is 2 times xy conjugate. Yes. But And this is norm of x squared plus norm of y squared plus 2 times, unless we prove that this is greater than 0, because on the left side what we have is so we have some xy conjugate term here. How do you prove that this is greater than 0? So for the same vector, we know that it's greater than 0 and it's in the real line. So there it's fine. But if it's x and y, x and y, two different vectors, how do you prove it's greater than 0? I'm not really sure. Okay, how do we prove this? We have to refer. Just a second. I think we should have used Cauchy-Schwarz inequality. The third property, how do we prove this, is using the Cauchy-Schwarz inequality. What does Cauchy-Schwarz inequality say? So far, what we have proved. Norm of x squared plus norm of y squared. Okay. By Cauchy-Schwarz inequality, we have now modulus of inner product between x and y is less than or equal to norm of x into norm of y. And there's a half, right? So if we use this property here, then this is Cauchy-Schwarz. So which is actually equal to norm of x plus norm of y, the whole squared, implies norm of x plus norm of y. I mean, norm of x plus y is less than or equal to norm of x plus norm of y. This is the triangle inequality. So we have to apply the Cauchy-Schwarz here. I think there is some mistake here. So is it the inner product while we are adding it? That also I have to recheck. Okay, please recheck it from your end as well. So this is, so we've proved one, positivity properties, non-negativity and positivity properties, homogeneity properties, and finally the triangle inequality. We expand it initially, then we use the Cauchy-Schwarz property. So let's conclude the session here.